Hello, everyone, and welcome to the webinar. We will start in just a few minutes from now. Thank you. Hello, everyone, and welcome to today's webinar. Today's webinar is part one of a series of webinars on building machine ID for mill-turn machines. And the webinar will be given by Marina Vilkina. But before we start the webinar, Emil Somich would like to say a few words to everybody. So, Emil, go ahead. You're unmuted.
Hello, everybody. Glad to have you here. We have a big crowd listening to this webinar, and it's very important. As you know, our strategy is to become number one in supporting advanced mill-turn and Swiss-type machines. And that's why it's very important that each one in our team, both the technical and salespeople, should understand these machines much better. Marina Vilkina is our expert in this field. She's coming from St. Petersburg, Russia, and she was going to give a series of webinars. So whoever attends the first webinar should continue and watch the coming webinars. Enjoy.
Okay, thank you very much, Emil. And Marina, I will make you the presenter, and you can go ahead and start. And don't forget to unmute yourself. By the way, before you start, I just want to mention to everybody, this is being recorded and will be available to everybody later on. All right, Marina, go ahead.
Thank you, Sydney. Can you see my presentation on the screen?
Yes, we can.
Okay, I just want to check everything is okay. Hello and welcome to the webinar. This is the first session in a series of webinars we are going to present online. The main issue of the series is to show a sequence of steps in the way of building machine ID for mill-turn and Swiss-type machines. A couple of first webinars will present basic things about machine ID for mill-turn. You may be familiar with these rules, but I would like to repeat it and to be sure it is clear before we will move to multi-channel stuff. This webinar will cover a list of very important basic things concerned every mill-turn machine. I'm talking about preparation of machine data, and key of success in building machine ID lies in understanding of links between a real machine, machine manuals, and machine ID created in SolidCAM. Today we will take a look on a concept of part table and tool table, and we'll see a couple of examples of real machines. Before I will go further, I would like to pay your attention and remind about post-processor materials, which are always available for you. First of all, this is the SolidCAM help. You can find the machine ID functions in the machine section there. Also, we have the GPP tool help documentation, which has detailed description of all system variables and new functions with good examples inside. You can go to the SolidCAM site and find in the documentation section, you can find the machine ID reference guide. And also we have the series of previous webinars recordings available, and they're describing post-processor features. Let's move to the first item of today's webinar. The main challenge about building a multi-turn machines in SolidCAM is connected with the multifunctionality of such kind of machine tools. The key of success lies in the analysis of the machine structure and grouping its functions accordingly. A quick review of functional parts of mill-turn machines and their purpose of use will be described below. We will start from the concept of part table and would like to name a list of functions of mill-turn machines connected with the part table. First of all, the name of the part table that we are using inside the mill-turn machines and in mill-turn terminology. We can call this the part table or turning spindle or just spindle. The name the spindle will be used for the other devices too, so be careful when using this word naming whatever device you would like. The purpose of use the part table, first of all, it is part clamping and unclamping, part rotation in turning mode for turning operations, part angle position for index milling operations, for part simultaneous rotary movement for simultaneous operations, and it may be linear movement by Z direction or even by X and Y direction. It depends on the machine complexity. Let's talk about part table position and how it is defined in machine documentation. Here I have a couple examples of machine diagrams from manuals showing relevant position of devices inside cutting zone. You can notice that there is two basic points for part table, or we can call it spindle, on the diagram. The upper chain of dimensions is showing the turret position relevant to back side of a spindle, and lower chain of dimensions are connected with back spindle or tailstock if the machine hasn't back spindle. That means main spindle is the basic device to construct an axis layout. But confusing thing is that both diagrams are showing two different positions on spindle for the upper and for the lower dimensions chain. We can get an answer on this misfit if look more closely on spindle itself. When you have a deal with lathe machines, please remember that they can be equipped with different types of clamping devices, and dimensions of these devices are not equal and may vary. But your basic assembly point shouldn't depend on type of clamping device. That is why normally the point is located at the back side of the clamping device, exactly on the face of the spindle nose. You can see that current diagram is showing it is very clear. We can see our dimension chains both have the one unique basic point at the back side of the clamping device. Therefore, the main issue about basic machine and main spindle point is that it cannot be located on a removable device. It should be a part of machine. Now let's see how we can handle with this inside machine ID. The first feature I would like to notice is two positions that can be set for a part table inside machine ID. The basic position is part table position, and the second one is the part table station. We can assume, according the machine manual, that part table coordinate system is spindle noise and part station is clamping device noise. The last one will be relevant. What means the station coordinates are not absolute. We are using a relative coordinate system for this point. And this is very helpful because you can input the length of clamping device from a manual or from fixture catalog to a position field of the machine ID. Let's go further and check how these figures will influence on a setup window of CAM part. From the version SolidCAM 2018, we got a very convenient and easy to use machine setup dialog window. Together with machine preview dialog window, it will help you to start your project and answer questions about stock, position, and safety areas. The position of part table station will have an effect on a part position in setup window. It is recommended to create the same part location as it will be on machine. Find out how customer measure it part on machine during clamping. You will be able to repeat this process using mark position and part table station position. And then user will be able to just input measured data to SolidCAM setup window. Let's move to the CAM part and see the link between part table position and setup window. I'm just going to the SolidCAM project window. Because of limited cutting zone and complex tool posts inside mill-turn machines, we always have a chance of gouge with clamping device. That is why we recommend always use setup window before adding operations to the project tree. SolidCAM has a special settings for mill-turn projects, so you can add setup header automatically. Let me show you SolidCAM settings window. Here we have automatic CAM definition section and mill turn tab inside it. Just make create machine setup active and you will always have your setup header inside the project tree. It will appear automatically. Now let's take a look on machine ID itself. I have a preview window here, and here we have a machine with two spindles. They have the same type of clamping devices. It is called collet chuck. But because main and back spindle noise are differ, the size, diameters and lengths of chucks are differ. The main one is bigger. As you can see, positions for both spindles. Let me just expand both positions for the spindles and show you the positions for the device. Pay attention that I'm going to the coordinate system of the device. The both spindles are defined according absolute coordinate system. For the main, we have 0 here, and for the back, we have 713 millimeters. You should the distance with the sign between two spindles noises is measured on the machine, and you should do it very carefully because these figures will be used during the part transfer. So this distance should not be located on a removable device. Let's go to the station positions. And station positions has the coordinate relative to the spindles. Here we have for 165. That means we have a distance between the back spindle face and spindle face 165, and here we have the figures, but they have a sign. The sign depends on the coordinate system. We will talk later about coordinate systems and how to set up it for the mill-turn machines. Okay, Sydney, I think you should unmute. Sorry. Okay. Now let me open the setup window, and we will see how it is an influence of the machine ID on a setup window. I already have my stock and my mark position created for this project. By default, all Z fields inside the machine setup, this field and that one, 0 for fixture and for the part position. Collet chuck has no additional fixtures. We have none here. So I leave fixture Z field as a 0. But my part Z position can be 0 on a real machine. If I will zoom in chuck face area, you will see Mark 1 position has the same position as a part table station, but also you will see a piece of stock out from the chuck, the main chuck. Now I will change the position of the stock just with my mouse wheel. And you can clearly see that Z field is the distance between part table station and part mark position. It doesn't takes into account my stock face offset. Now let's imagine we have a jaw chuck device. Let me go back to the presentation to show you the next slide. JAWS is a very important element of machine setup system. Each lathe machine, if jaw chuck is used, has a set of jaws of different configurations and dimensions. A customer can even machine his own jaws. That means we should have a possibility to add jaws of different types, position them and adjust stock accordingly. Let's look on a machine with jaws chuck and its setup in SolidCAM. I just open a new project with the new machine which has jaw chucks inside. And I'm going directly to the setup window. Here I have jaws are already defined, and I would like to show you that jaws position and part position are independent from each other. Both of them measure their position from spindle station, which is defined inside the machine ID file. So here I have two sections. It's a section about clamping fixture, and so I can move my jaws accordingly. I would like to say that jaws can have a different Z position. It depends on chuck, on jaws. The position and configuration can vary. And here I have the field to position my stock inside the clamping device and adjust it with the that means we can use a face of jaw chuck as a spindle station in machine ID file. This station will be in EQ 0 point for our machine setup window and for the fixture and for the part position. I would like to add one more note to this item. You can use data from setup window not only for simulation and preview. Most of modern CNC has visual functions, even 3D and C code check before cutting. But to use this possibility, you should describe stock dimensions and stock position in chuck inside NC code at the very beginning of program. This code is not looking as ISO code. It is a set of internal CNC commands, but you can easily take a CNC template and just put figures directly from setup SolidCAM setup window to this template, and customer will get the possibility to double check of outputted code on the machine. I will go back. Let me close it. I will go back to my presentation and add a couple of comments about Spindle. table position for subspindle is defined with the same manner as for the main. The direction for back spindle may vary. It depends on machine and customer working style. We will look more closely on axis directions during the next webinar. Now let's consider a tool table device. Tool table device can be called with different manner, depends on machine and the machine manual. We can call it like a tool post or tool spindle. The purpose of use, we should clearly understand the purpose of use for the tool table on the machine, and we can support all these functions inside the machine ID, and we should double check that everything is working before give this machine ID to the customer. First of all, the first purpose is of course tool positioning. The second one, our tool table or tool post can have a linear and angular movement. Also, we should support the issue of mounting tool using different holders. Because of holders, we can have the completely different position of the tool than without them. And also we can get the information about tool offset data from our machine ID and from the machine preview window using the current version of machine ID. And of course, we can support the milling and toning modes during cutting with different tool tables. This is a very important thing about mill tone machines, because milling and toning modes have their own sets of the commands in G and M codes and different types of speeds and feeds. So we can define the modes, these modes for the different tool posts. Here I have several examples of tool posts from the number of real machines. I would say complex mill-tone machines or Swiss type machines can have a mix from different tool posts with different functions. Despite all tool tables are looking very different, we can group them on three types. And you can apply a certain type inside machine ID file. Here they are: rotary type of tool table, spindle type as for milling machines, and the most popular for Swiss type machines, it's a linear type of tool post. I believe that the most complex question is a definition of tool post position, because it is not so obvious as for the part table. You may need several sources of data to completely define tool post position. You will have to get data directly from machine, compare it with diagrams from machine manual, and get some missed information from machine 3D assembly. Here you can see a common example of searching of axis position on Swiss type machine. The vector of x-axis of this machine has a vertical direction and y-axis is perpendicular to it. So we are moving gang tool post to its maximum limit position and note y1 machine coordinate. After that, the distance between the center of spindle and tool post should be found. Because 290 millimeters is not the distance, it is the machine coordinate in a limit position for the gang tool post. Let's study what is stroke, reference position, axis limit, and tool post position. The most familiar and commonly find machine data is strokes diagrams. Most of the machine manuals have information about machine strokes. Machine strokes is a distance between maximum and minimum position of machine device, or between maximum and minimum position and reference point. Machine strokes doesn't have information about real machine coordinates in maximum and minimum position. They can help to see a volume of cutting zone. And as you can find from the current diagrams, this volume is depend on tool mounting. The next slide, this slide is about tool post and machine reference point. A reference point is a point which is known for all machine devices. It is independent on part 0. There is a special G-code to send any machine device to its reference point. Reference point is programmed with internal machine parameters, and it can be changed. In most cases, machine needs to start and finish from the reference point, and reference point is useful because it is never changed on the machine. A couple of words about reference point for Milton machines. Machine coordinates of device may not be 0 in reference point. Usually, reference point doesn't equal to machine maximum and minimum limit. The best way to find device reference point is to measure it on a machine. Let's go back to the machine ID file and see how we can complete tool post position data. Definition of tool post position in machine file depends on tool post type, device machine 0 position, and device reference point. You can input all this data accordingly after measuring and checking it on the machine. Here I have a rotary turret type of the tool post. And for this type of tool post, a turret center position is commonly used. Do not forget that this is not a maximum or minimum position, and this is not reference position. This is 0 position of device in machine coordinates. You can input information about reference position in a special field for axis, but not for device. Axis home reference parameter, it is the distance between rotary turret center position and turret reference point. Home reference coordinates should be equal to machine coordinates of CNC display when turret is in its home position. It may be 0 if turret reference position on machine is 0 when you display it on machine in machine coordinates. But most of a machine, especially complex Milton machines and Swiss type machines, don't have 0 in this field. After you define the tool post position and its reference position, you can enter data for minimum and maximum limits. They are entered for axes, but not for devices. These limitations will be used for machine preview, MCO operations, and for machine simulation. Let me show you quickly what I'm talking about. I'm going back to my project and my machine with a chuck, with jaws, and I will to show the difference between all these definitions, reference point, the 0 station, and so on. I will show you it on a z-axis for this machine. Let me put my z-axis to 0 position. I'm just input 0 here. And it is clear that this is out of limit and it is impossible to achieve this position on a machine. How I have found it? I asked to move turret to its minimum Z position. I have it here, my minimum Z position. and notice the machine coordinate from CNC display. So 154.67 is the real coordinate on a real machine, which I got from the CNC display. Then I just measure it a distance between chuck face and turret face. That's what I can get on a real machine. I added a distance between the turret face to the turret center center point, because I know this because of the documentation, the description of the turret dimensions inside, and move turret center inside machine assembly on these figures. I move it towards its zero position. It's obvious that zero position is somewhere here. Till the turret reached its machine zero, which is out from cutting zone for this particular machine. Then I added positions for axis home reference, which is here. It was easy because home reference is a point in machine coordinates. I took it directly from the machine screen, CNC screen. The last step is the limits. I got them from the machine too. Here I have it, my limits, just directly from the machine. Notice that machine manual has no information about machine coordinates for devices. Do not lose an advantages which customer can get using a real machine data inside SolidCAM, and build your machine ID based on machine data and not only on the manual. Let's go back to the presentation and check other tool post types. The idea of finding tool post position using a real machine is true for spindle and linear turret type. Spindle tool post on the mill-turn machines has a rotary axis, so be careful and define a rotation point before defining the spindle type of turret. The rules for spindle type are the same as for the 5-axis machines definition. The most interesting and the most flexible tool post type is the linear type. The easiest way to define a linear spindle is to use 3D model of machine. In a machine assembly, you should create machine 0 point, as it will be in a machine ID, and put linear spindle to its machine 0 position. And then you can define the turret position and add tool stations accordingly to it, or leave turret position as a 0 and define tool station accordingly to machine ID 0. I will show a couple examples of defining linear tool post in the next webinar. The next session will cover building access issue and questions connected with defining coordinate systems for different devices on mill-turn and Swiss type machines. Thank you for your attention, and this information was useful, and now you have an idea how to start machine ID for your particular machine. So Sydney, are you here?
Okay, Marina, thank you very much. I see there are 2 questions. If you see the questions, I can read them out also to you.
Oh, let me check.
Okay,
No, I'm afraid I'm not.
okay. Well, one question is, the first question is, why is the subspindle defined with the same Z direction as the main spindle when the direction in the machine is different?
Okay, we will talk about these questions later on the next webinar. It's a quite volume question, I would say, because as I mentioned in this webinar, it really depends on the machine, on the style of working in which customer working, and I will mention our new rules of creating the machine ID files. So just be patient and wait for the next webinar, please.
Okay, and there's one more question. Okay, he wrote it both in Russian and in English, so I understand the English part. It says usually it is necessary to define position Mach 1, position 1 concerning the first plane jaw chuck, but not a mirror of a spindle. How is it correct to make if jaw chuck has various sizes?
Is it a question about the Mach position for the back spindle? I'm not clearly understand this sense, I'm afraid. The axis direction for the Mach 2, is it a question?
I can't tell.
Let's try again.
Okay, let's see. Let's try this again. He's asking for. He will. I will unmute him, and he will ask the question exactly. Hold on a second. Milkan M. Just a second. Okay, I see two of them here. Okay, Milkan, I believe you're on. You can talk.
Марина, добрый вечер. Андрей Благодаров.
Okay.
Меня слышно?
Да.
Вопрос следующий. Значит, относительно основного шпинделя. Заготовка вытягивается из кулачков, а в солидкаме она задается от зеркала шпинделя расстояние в сетапе, в сеттинге.
Okay, Marina, please translate the question into English.
I'm trying to understand the sense.
Or if you want, you can take this. If you can take this later offline to explain it to him.
Yes, I think it will be better.
Okay. So Milkan, so later on after the webinar, you can speak directly to Marina, and she can ask you, and she can answer the question for you. Okay. Thank you again for joining the webinar.
Ответа, как всегда, нет от солидкама. Спасибо.
Okay. The webinar has been recorded, and it will be available to everyone later on. And hopefully we'll see you again in the next webinar. Take care, everyone, and have a great weekend. And again, thank you again, Marina.
Oh, thank you. Goodbye.
Bye-bye.